When you're driving in a car, your speedometer tells you how fast you're going. But if you know how long you've been driving, did you know that you can calculate how far you've traveled? Hi, in today's lesson, we're going to discuss average speed and velocity. So first, we're going to go through some terminology. So motion is the movement of an object from one position to another. And most objects in the natural world move in non-uniform motion. We don't go in an exactly direct straight line, and we don't move at the exact same speed the entire time. Motion can only be considered uniform when an object is traveling in a straight line at a constant rate. This ideal situation rarely occurs for long periods of time because there's friction and air resistance, which decrease the rate of travel. Most objects turn during their motion, which causes an object to change direction. However, when an object is stopped, it's considered to have uniform motion because its constant speed is 0 meters per second. The average speed, which is v with no line over the top of it, represents the distance traveled over time, where delta d is the total distance traveled and delta t is the elapsed time. So the equation from your formula sheet is v equals d over t. And we can rearrange this formula to solve for distance, and we can rearrange this formula to solve for time. So where we have d is equal to v times the change in time, and t is equal to the change in distance divided by the average speed. And so with that equation rearranged, we can find in any equation the distance traveled, the time elapsed during travel, or the average speed. So speed is a scalar value, which means we don't need to imply direction, but we do need to include units. So when we don't need to do direction, we don't need to do positive or negative, north, south, east, or west. But we want to include the units, either meters per second or kilometers per hour will typically be the two that we're going to work with. So instantaneous speed is the speed an object is traveling at an exact moment in time. So let's say we drive from the south end of Edmonton to the north end of Calgary, and our average speed for the trip is 110 kilometers an hour. But our instantaneous speed, when we drive through Red Deer and we had to slow down because there's traffic, we might be traveling at 80 kilometers an hour. Or when we're passing somebody along the highway and our speedometer ended up reading 120 kilometers an hour. So we can see that the d in distance doesn't have that delta symbol in front of it because we're not talking about a change in distance. And our t also does not have a delta in front of it because we're not talking about a change in time, just a specific time. So when we're looking at the distance traveled, it can be found in two different ways. We can add up all the different distances we traveled. So we went forward 3 meters, we had to turn around and go back to the start 3 meters, we crossed and we went home, and then we went to our friend's house in the other direction. So we traveled 3 meters out, 3 meters back, and 3 meters in the other direction for a total distance traveled. Or we can rearrange the speed formula. So you can go v equals d over delta t, and velocity equal, or the change in distance equal velocity multiplied by time. It depends on the type of information we're given in the question. In the question where we're given, this is the places we traveled, adding them up is going to be more efficient. But if we're given a question where we have a velocity and a time, using the mathematical formula is more efficient. So, for example, one looking at distance. A driver talks on the phone for 36 seconds while she's driving at 100 kilometers an hour. How far did she travel in this time? So we can either convert 100 kilometers an hour to meters per second, or we can turn our time into seconds. So for this equation, we took 3,600 seconds in 1 hour. So we took 1 hour divided by the 3,600 seconds, and we got 0.01 hours. So after rearranging the velocity formula, the speed formula, we have calculated that she traveled 1 kilometer in the time that she was talking on the phone. Okay, example 2. if the speed and distance traveled by the moving object is known and the time elapsed can be found. So we have been given the speed and the distance. We're going to try and find the time that has gone by. So standard headlights allow a driver to see 60 meters ahead of the car. A car is traveling at 120 kilometers an hour. How many seconds does a driver have between what they see on the side of the road and when they pass that person? So here we turned our, that's for the end. We converted our 60 meters into 0.6 kilometers divided by our speed at 120 kilometers per hour. We came up with 0.05 hours. Okay, and then we took that 0.0005 hours multiplied by how many seconds are in an hour, and we got 1.8 seconds. So from the time that you see somebody or something in your headlights, you have about 1.8 seconds traveling at 120 kilometers an hour before you pass that object. So let's look at different converting factors. So we want to convert between different units, whether it's centimeters to meters, seconds to minutes. We're going to look at converting from larger to smaller and smaller to larger. So when we look at inversely proportional ratios, a larger unit will have a smaller number. So we have kilometers, which is a larger unit than meters, and it's going to have a smaller number. So 3 kilometers will be things like 3,000 meters. And a smaller unit is going to have a larger number. So 100 centimeters is 1 meter. So these conversion factors are in your data booklet, and this is what we're going to be referring to today. So we have our base units would be things like liters, grams, meters, and moles. And then the higher up we go on the chart, we're getting to be larger units, and down on the chart, we're getting smaller units. So to convert to a larger unit, you always divide, and to convert to a smaller unit, you always multiply. However, we're going to go through in a ratio format so that you don't have to remember, oh, do I divide or multiply? But we're going to do crossing off of units so that we always have the correct math. Okay, so here we're going to go through 245 kilograms to grams. So we're going to have 245 grams. And we're going to multiply this by, and we want to have grams on the bottom. So we have 1 kilogram is 1,000 or 10 to the power of negative 3, because we go grams to kilograms. Okay, but I'm just going to use 1,000. So I'm just going to use 1,000 there. Then our gram unit crosses off on both of them. We go 245 divided by 1,000. We get 0.245 kilograms. Okay. So don't have to worry about multiplying or dividing. We just always want the units that we want divided by the units that you have so that we can cross off. So it's have multiplied by want over have. Then we can cross off the 2 units that we have and we find the units that we want. Okay, so we're going to go with 2 moles times, I have mole down here and millimole here. So 1 mole is 1,000 or 10 to the negative 3 moles. And this is equal to 2,000 millimoles. Okay, so again, these units are crossed off and millimoles is left behind. Okay, so this is like H is hectometer, so it's not something that we often talk about, but we just go 3.5 hectometers times, we want meters up here, so 1 hectometer is going to be 10 meters. So these cross off. And we end up with 35 meters. Oh, sorry, it should be 100 meters. So 350 meters. Okay, lastly, we're going to start with 4,500 nanometers. And we're going to convert this to meters. Nanometers on the bottom. So 1 meter is 10 to the power of negative 9 nanometers. And so we have the answer is where's my pen? There we go. 4.5 times 10 to the negative 12 meters. So a much smaller number in meters. Okay, so those are conversion factors. And like I said, if you keep that, have the unit that you have multiplied by the unit that you want divided by the unit that you have, you'll always end up with the unit that you want. Okay, so we also are going to look at converting between kilometers per hour and meters per second. So in science, most speeds are given in meters per second. However, in everyday terms, most people use kilometers per hour. So to convert between meters per second and kilometers per hour is more different because we have to convert both the distance and the time. So here we've converted our hours and our seconds. But to simplify, and you can write this quickly in your data booklet, to convert from meters per second to kilometers per hour, we're going to multiply by 3.6. And to go from kilometers per hour to meters per second, we're going to divide by 3.6. So when we're going 2 hours to seconds, so we're going to go 2 hours. Okay, and we could do many. So 2 hours, I'm going to put hours on the bottom. So 1 hour is 36 minutes times 1 minute is 60 seconds. So I'm going to go 2 times, it should be 60 times 60 is 7,200. So this one here, I was thinking still about the conversion, so that's going to be 60. And so 2 hours to seconds is 7,200 seconds. Okay, 4.5 minutes to hours. So 4.5 minutes times 1. So we have 60. Minutes in 1 hour. So we end up with 0.075 hours. So this was 0.5 hours. Okay, now 100 kilometers an hour to meters per second. So we're going to divide by 3.6. And we get 27.78 meters per second. And then 18 meters per second. I'm going to times that by 3, multiply that by 3.6. And we're going to get 64.8 kilometers per hour. So again, write that meters per second to kilometers per hour conversion in your data booklet so that you have access to it when you're doing your practice problems. Okay, so the appropriate conversion to conversion factor to determine how many minutes in a week. And again, we're going to do this one step at a time. So we said 1 week has 7 days. So then we can cross off week. 1 day is 24 hours. 24 hours has 60 minutes. So there's 10,080 minutes in a week. And we can do that one conversion step at a time. Again, always units that you have are on the denominator divided by the units that you want are the numerator. So if you remember a little bit ago, I said that speed is a scalar quantity. So it asks how fast are we going, but it doesn't say in what direction. And this is the same as temperature and distance. However, in physics, we use a lot of vector quantities. And vector quantities ask how much and in what direction. For example, velocity, acceleration, and displacement. So the symbols for vector quantities are written with a single arrow above them. And when we have a vector question, we want to give them an answer in a positive or negative direction or a northeast, southwest direction. So if we recall our distance traveled when we were going 3 meters to the right, turning around and traveling back to where we started, and then 2 meters to the left, that object has traveled a total of 8 meters, and that's the distance traveled. But if we look at the displacement traveled, displacement is a vector quantity. So we want to know how far that object has moved from its starting point. So if it's traveling with uniform motion 3 meters to the right, this would be positive 3 meters. Then it turns and travels 3 meters back to the left. So it'd be negative 3 meters or 3 meters left. And then it travels an additional 2 meters left. So 2 meters left or negative 2 meters. So we can say that this object has traveled negative 2 meters displacement or 2 meters left. Both are acceptable when we're talking about vector quantities. So the unit always, our answer always has to have a direction or a positive or negative unit in it. So we can travel 100 kilometers per hour west, 100 kilometers per hour south, and so on and so forth. Now, because direction matters for vector calculations, certain directions are either positive or negative. So up and east or right or north are considered positive. So if we throw a ball up in the air, it's positive displacement. If we travel north, it's positive displacement. South, west, left, and down are negative displacement. So if a ball is falling back to the earth, it's negative displacement. If a object is traveling south or west, it is negative displacement. So again, you can give letter directions or a positive and negative in your answer. So here's an example where we're going to do some sign conversion. A trucker travels from Edmonton to Calgary to Edmonton to make a delivery of 360 kilometers, then turns around to make a delivery in Red Deer. What is his distance traveled and what is his displacement? So if we look at distance, our direction doesn't matter. We take the first distance of 340 kilometers and the second distance of 180 kilometers to have a total distance traveled of 540. However, his displacement starts when he leaves Calgary at 360 kilometers north, and then we take negative 180 kilometers south, and we come up with a total distance traveled of 180 kilometers north. So here's our little diagram of where he traveled, and we can see that the displacement between Calgary and Red Deer is shorter than his total distance traveled. So velocity represents displacement over time. So the delta V, or the V with the little arrow over top of it, is velocity. V without a little arrow is speed. And when you have the velocity arrow, we must specify direction. So meters per second, west or south, or plus or minus. And they're rearranged the same as the speed formula. So delta D, or displacement, is equal to velocity multiplied by time, and time is equal to the displacement divided by the velocity. And if we're calculating velocity, we must use displacement. If we're calculating for speed or distance, we can use those ones. But if you're using vector quantities, all of them must be vectors. If you're using scalar quantities, all of them must be scalars. So here we're going to find the average speed and velocity of a ball. So a ball rolls 10 meters in 4 seconds, bounces against a wall, then rolls 5 meters in 2 seconds. What's the average speed of the ball? What's the velocity of the ball? So velocity requires displacement, and speed requires distance. So if we do the speed first, so it traveled an original 10 meters, 5 meters for total distance traveled of 15 meters. But that displacement, we have 10 meters in a positive direction, 5 meters in a negative direction, so a total distance of 5 meters traveled. And so that you can tell this is greatly going to change the velocity of the ball and speed. So now looking at speed and velocity. So with speed, the time is going to stay the same. We have a total time of 6 seconds. And with our speed, we had a total distance traveled of 15 meters divided by 6 seconds. So our average speed was 2.5 meters per second. With velocity, our displacement was only 5 meters to the right. And so when we divide that by the 6 seconds, we end up with a velocity of 0.83 meters per second to the right. Now, this one might be more accurate for our vision of what we saw happen, but in physics, this is our most accurate answer of the average velocity of the ball. So that's our introduction to scalar and vector qualities and speed and velocity calculations. I hope you enjoyed today's lesson.
If you enjoyed this video, check out our website, online.plrd.ab.ca, and visit us on Facebook, Prairieland Online Academy. You can find out all that's going on with Prairieland Online Academy.